So quantum mechanically, this can't be explained because classically this can't be explained because classically we think that you have something orbiting in some trajectory that defines angular momentum about some axis that we can then identify. We can identify the axis that corresponds to the angular momentum, the orbital angular momentum, precisely. But here, what we've learned um, is that we can't identify the precisely what the orbital axis is, because if we could, then LZ should be able to account for all the angular momentum in the system, the orbital angular momentum in the system. Okay, so why is this? Well, it turns out if L were equal to, if the Z component of the angular momentum could account for all the orbital angular momentum in the system, so if this were true, if L is equal to LZ, then that would imply that Z equals 0, and therefore that delta Z equals 0, and also that the Z component of the momentum, not the angular momentum, the Z component of the momentum were equal to 0, and therefore that the uncertainty in the Z component of the momentum is equal to 0. But by the Heisenberg uncertainty relationship, we know that we can't simultaneously have delta Z and delta PZ equal to 0. They have to there's an uncertainty relationship here which requires the product to be greater than h bar over 2. Okay, so this picture should help us understand this. If L were equal to LZ, that is, if the Z component of the angular momentum accounted for all the orbital angular momentum in the system, then we would have a situation where the particle, let's call it an electron, we're orbiting completely in the xy plane. Okay, because that's the only way for the projection of the angular momentum onto the z-axis be equal to the total value of the angular momentum. Okay, and so this means that the particles would always be orbiting in the xy plane. So that means z equals 0, and it would never move outside that plane. That is, it would not have any component of the motion perpendicular to that plane, which means that pz equals 0. So what this tells us, okay, is that by requiring LZ, or by limiting LZ to be less than L, not equal to L, but strictly less than L, then that basically leaves us some uncertainty in the trajectory of the particle, so it can vary. Its motion can have a out of plane component, which then would lead to a uncertainty in the projection onto the z-axis. Okay, so in some sense, as it's orbiting around, because it has to have some out of plane motion, then by the uncertainty principle, then these planes, the planes that define the orbital motion, have to sort of wobble, which leads to what we call a precession, if you will, of the orbital angular momentum about the z-axis, and so the projection is not going to be equal to the total value of the angular momentum. Okay, and so that's a deep quantum mechanical result that again goes back to the uncertainty principle, which, as we've seen, is an absolutely fundamental part of quantum mechanics. Another way of describing the situation is that the individual components of the angular momentum, Lx, Ly, and Lz, do not commute. That is, the operators which correspond to Lx, Ly, and Lz don't commute. So if you apply their operators in Lz, Lx minus Lx, Lz, that won't equal to 0. Remember commutation. And so there's an uncertainty relationship between the components of angular momentum, meaning that we can't know two components of the angular momentum precisely at the same time. So we can know one component, but we can't know two components precisely at the same time.